meeting's being recorded, so if anyone has a problem with that, please let us know. But I'll share my screen and we can start going. Okay, can everybody see that screen? I'll just get rid of this participants. So yeah, so this is our, I think it's our third one we've done. So just to let you know, we are recording this and we'll make copies available afterwards. And I think we're quite happy if you ask questions during or after the presentation. We're quite happy with both of those if there's a burning question. So what we're going to do is I'll do a quick introduction and update on what we've been doing. David is going to show some work around container packing optimization, which we've been up to. And Jacob is going to run through a more advanced approach to optimization when you've got prime movers and trailers. And then afterwards, we should have a bit of time for questions or further discussion. So we may have covered some of this in the last meeting, but just to give you a bit of an update, we have this project around a decision support for the path to net zero happening with it's called the Race to 2030 CRC, which is a reliable, affordable and clean energy. So that project's ongoing. About 6 weeks ago, we got a very important project, which I can't say too much about, but you will in the future, around integrated production scheduling. We've done quite a lot of work in production scheduling, but this is quite a big project where we have the opportunity to build more of a platform. We've got a couple of things happening in the UK with transport around car transporters and distribution. And we've also put together a couple of proposals with CSRO in Chile, who are interested in helping us getting into the South American market, which again is a very interesting one. We've put together a proposal to do further collaboration with Monash University around optimization for chemical processes, which we'll get a decision on that in October. And the final one, which comes as no surprise to probably a few of you, that everyone's talking about quantum computing. And we put in a proposal with a company called Archer, who developed hardware for quantum computing for New South Wales transport. That didn't go very far, but we're looking at other opportunities for using quantum computing to make the optimization even faster, although I'm not entirely sure that it needs to be that much faster than it is, but you never know, problems get bigger and customers' requirements get more complicated. So quite an exciting few months. So today, today I'd like to introduce David to talk about some work we're doing on container packing optimization. And then Jacob will talk about the prime mover and trailer optimization. So I will come out of my, unless there's any questions at this point. Okay, I'll come out of my screen share and let David get in.
Alan, if I can ask, this is Anuj from Singapore. Your production scheduling, are you able to tell us which industry it relates to?
Well, the reason I can't say too much about it is it's a defense project.
Okay, all right, that's fine.
But look, it's advanced manufacturing.
Okay, fair enough. And I've been working, as you know, on the steel industry, and we've been going through a lean patch, but there's renewed interest again. So that's why I was raising this.
Yeah, I think it's generally applicable.
Okay. Thanks.
I'll just share my screen now, if everyone just bears with me. There we go. Perfect. Okay, so what I'm going to be talking to you about today is optimal container packing. So this is a product that we've developed after a client came to us with a particular problem involving packing rolls or cylindrical shaped rolls of like a sheeting material. And the main problem they had was working out both, how many containers they need to pack what they must pack, which is in the order, but then utilizing that additional capacity left to pack kind of residual products that are in the warehouse that aren't as urgent, but still need to be moved between various locations. Cool. So with our container packing, we've got a series of items to be packed. We've got a set of containers to be used for the packing. We've got various item and container constraints. So in academia, this is often referred to as the three-dimensional bin packing problem, if anyone really wants to look up the kind of real nutty, meaty parts of it. But it's a very complicated problem, as much as it seems relatively simple to put things in. In computational theory, it's considered a very difficult problem. So obviously we've got our items. So these are the objects that actually require packing. So the items have a shape. So currently we've implemented using boxes or kind of rectangular objects, but we can also handle cylinders. So items have a dimension, depending on the type of shape they are, length, width, height. For cylinders, we've also got a diameter. They have a weight. Now there's also a profit associated. So this is basically what's the reward for packing the item. So this could be an actual monetary, so the profit from the actual item, or it can be an arbitrary assigned to that particular item. So some of the constraints that we actually have for the items are which rotations are allowed. So obviously these items can be rotated in space. So is the item fragile? So this means that nothing must be placed on top of it. Is the item heavy? If so, it can't be placed on top of anything else. And obviously we can expand these if additional ones are required. So for instance, here, just looking at the examples for a cuboid. So these are rectangular boxes. We've got 6 different types of rotations. With cylinders, obviously some of these are a bit redundant because you're just rotating the cylinder and it doesn't actually change. So you can specify in the input format with which types of rotations are allowed. So for instance, if you're moving something like electronics, like a television or laptops, things like that, you might not want to orient them in a certain way. And you can tell the optimizer to not use that orientation or rotation. So obviously we've also got the containers that require packing. Now, while this is called container packing optimization, it's just a box that needs to be packed. So this could be implemented also for trucks, any type of container or object that you can put items in and require packing. It doesn't actually have to be shipping containers. But in this case, they just represent the objects that are used to hold the packed items. So containers have dimensions, obviously, and they've also got a cost associated with them. So the idea is, particularly if they are shipping containers, how much it costs to, if you pack that container, to maybe rent the container, ship the container, all of the above. So the constraints associated with them are the maximum volume and the maximum weight that can be packed. So some of the advantages of using this type of methodology in terms of an algorithm to do the packing is the speed in which it runs. So to hand pack containers in terms of building plans is quite labor intensive. It's also very difficult to check you've met all of your constraints without really running through every single item that you've packed, and making sure that if it's a heavy item, you've not put it on top of anything, things like that. We also offer 3D visualization and the ability to kind of simulate unpacking the container to see where items would actually be placed. So there's also options for using this as a standalone application, which I'll take you into after this, but it can also be integrated into your existing systems. It's also the ability we can customize this depending on your requirements, and for any further development that kind of takes place, you immediately have access to as the product grows and develops. So if anyone has any questions about what I've just gone through at the moment, I can address them now. But what I'll do is I'll actually show you the kind of web-based application that we've built to represent this and hold the data and run this software. Awesome. Can you see the, are you still on the PowerPoint or the?
No, we can see the browser.
Awesome, thanks. Thanks, Leslie. So the application just runs in a web browser. So here we've just got, I've just loaded up the initial system. Nothing's loaded yet. So the first thing I'm going to do is go ahead and just load a scenario. And in this case, we'll look at just some boxes. So just some sample ones I've created. So it's added these two tabs up here. The first one being your containers. So here we actually can manage, we can add new containers or modify or delete ones, but also modify. So if I double click here, it just brings up a little form to edit the container where we can define some of the parameters around the width, the height, volumes, cost, things like that. Similarly for the items, it's a lot bigger, obviously. All the various parameters associated with the items over here, you can edit them, remove items, add additional ones. So what I'm going to go ahead is just solve this. And in the background, it's just running. So it's just going to take about 10 or so seconds to run. Cool. So as it's finished here, the additional solution tabs have popped up, including the container solutions, the visualizer, and just a list of any unassigned items. The main thing that I'll show you is the visualizer. So this is a 3D representation of the packing, and there's various views you can do. At the moment, this is like a wireframe view. Useful sometimes if you've got particular different types of items. There's the empty space view and a solids view, which I'll show you here. So you can see the kind of packing orientation, and we can actually rotate the box kind of 360 degrees to have a look at where items are. If I hover over individual items, you'll see them appear in red. And by clicking one of these boxes, I can actually take the container back in terms of this is the list into which the items would be packed. So if I go all the way back to the start, we can see we've just got a single item. That's there. And as I move through, you can see how they would be packed as the solution progresses and you load more items in various orientations and configurations. So that's the representation with the cuboids or the boxes. What I'll do is I'll quickly show you a cylindrical solution as well. I just load, actually, I'll do the mixed because then we can see them both. So I'll just solve that. So with the cylinders, obviously the complication is that they need to be stacked in a stable configuration, and that needs to be, it can't just end up stable. It can't be just at the very end of packing. All through the packing process, it needs to be stable so that the, especially safety, you're not going to have things rolling off and landing on anyone while they're packing. So what we've done with this solution is basically implement checks to ensure that the resulting structure is stable. Here we go. So I jump to the visualizer again. Go to the solids view. We can see the various, you can see the cylinders packed in. And if I think go to heading 3, we can actually see that mix of items being packed. So we have some cuboids in there. So these are the boxes, as well as our cylinders being packed in that kind of network so that they're all either leaning against the wall or supported below. So this was the main use case that was built around the initial description of the product by the client, where they had these cylindrical rolls to pack and these boxes representing these additional products that can fill that empty space at the end. So yeah, this can also be, the solution itself can be exported to an Excel workbook, which will give you basically the packing coordinates of each item and where they should be packed and the orientation of them in the container. So before I hand over to Jacob, does anyone have any questions around the container packing?
Yeah, David, do you want to go back to the cylinders and just show the loading sequence to show that it's completely stable?
Sure. So jump back.
This is one of the issues of the customers to say, okay, it's all very well to tell me what I can get in the cylinder, but I need to be able to tell the people packing in that it's a stable loading sequence.
So as we step through here, we can see we build that base, and then the next item we place, I'll come around to this view here so you can kind of see them being placed. We place one on top in the space created between the two. Come across again, place one here that can lean against the wall. So part of this, the work involved with this was actually talking to the client about the ways in which they can load. So for instance, they're happy to allow an item to sit on top of one and then lean against the wall. If that was not allowed in other configurations, that could also be changed. So yes, the items are built up kind of top to bottom, left to right, and eventually you end up with the kind of fully utilized space in terms of, you know, there's no real additional places you could fit the cylinder, but the structure remains stable. Cool.
Thanks.
Max, I could see a little hand icon there. I didn't realize you could do that.
Hi, I have a question. Given all these constraints that you have, especially being stable at every step that you do at a certain item, have you been able to compute optimal solutions, or are you using some heuristic approach, incrementally adding the next best item, or is it a global optimum that you basically compute?
Sure. So this was it's basically the proof of concept for the client that when they had this problem, we showed that we could solve it, and the kind of what the kind of final solution might look like in terms of the visualization and things like that. In terms of optimality, I am pretty sure I can say this confidently that there is no optimal algorithm for the three-dimensional bin packing problem, the academic name for this. So there's basically you end up with a series of heuristic or approximation algorithms, of which I've implemented one here. Obviously, the potential there is to look at the various different types of algorithms. And I also, from reading some of the literature, there's, depending on the types of problems, sometimes different algorithms work better. But the eventual I guess end goal of a product list would be to end up with, you know, different choices and the ability to, you know, try different options to really maximize your packing and maximize your utilization of your containers.
So you don't solve the whole NP problem being given an optimal packing?
No, we don't run it all the way. No.
Okay, thanks.
I assume though that I know that obviously you talk about NP there, so that there are the various algorithms obviously have the kind of upper bound on, you know, kind of worst solutions and things like that. So that would be interesting to look at and to pick, you know, different types based on the various problems. Max, if you're finished there, I can see Paul's got a little hand icon as well.
Hi guys, just a question is, can you work out the spaces? And I'm thinking around you know, potential load restraint or movement within a container where you might want to fill the empty spaces with something to, you know, to deter the thing from, you know, wallowing around.
Do you mean like a buffer between items when they're packed, or
no? If you've got a gap on the top of that container there, for example, right? Yeah. And the container is on the ocean, right? It's going to bounce up and down. You don't want that to happen. You want to fill that gap with something, right? Yeah. Right. In order to kind of really, you know, force the thing to be reasonably,
like compact it down. We as part of the solution, it will tell you the kind of positioning of these items. So for instance, if I do like go to our cuboids here, they'll have a, you know, X, Y, Z for one of the corner, and it will tell you the opposites. So like where the furthest each side is. And so you will know at the height of each item, say if you're talking about above or to the side. We didn't then do really anything with that in terms of the client's description of once they've got the packing, they use various kind of blocks of foam and things, but they handled the wedging. But if I do show you the negative view here, we do have the ability to view the negative space.
Oh, okay.
Associated with the solution.
Yes,
so, yeah. So you can actually look at, you know, where you've got empty spaces and, you know, what. Yeah. So if you did see that, okay, you know, bits of foam, because you might be able to know yourself about packing which are okay, which aren't, things like that.
Where you're going to need and how much and so on and so forth. And my other question is, could you overlay this or with an unloading priority if you were carding for, you know, multiple, you know, customers, if you like?
The idea of, say, if this is the door at the front here, you want certain items to be closer to the front, and so we haven't implemented that as yet, but it was something that was discussed with the client, this idea of zoning almost, or this idea of, you know, items of a certain type, in which case this attribute could be first off or something like that, that they'd all get clumped together and at the front. So that's definitely possible.
Okay. I mean, the classic case is, you know, a retailer, you know, DC delivering to their stores, whatever, and doing a circuit around the stores, and, you know, store 1 is first drop off, store 2 is second, and so on. Therefore, I'm going to put my pallets accordingly, right?
Sure. Yeah, that's definitely something that could be integrated into the system.
Cool. Thank you.
Paul, I was going to just to interject. I think, as David made the point, this probably came from our work with fuel optimization. Is there is an integration between the loading pattern and the routing and scheduling. So, and there's also weight and balance, because containers can't be completely lopsided, because when they pick them up. So you've got, and we've already talked to some transport operators about how they reckon they're leaving quite a lot on the table when they fill a 14 pallet trailer that waits out. If you move the pallet like half a meter one way or the other, backwards or forwards, you can actually get another one on because of the weight and balance. A lot of people don't appreciate that. They think it's, if it waits out, it waits out. Well, it waits out on an axle, but it doesn't wait out on the complete vehicle, you know?
Yes.
There's opportunities to take this in a number of different directions. But the interesting thing is, a lot of this software is free, but it's totally standalone, and it doesn't do a lot of what we're doing. So the idea is integrate this within the overall transport scheduling and optimization.
Yeah. Very good. Brilliant. Thank you.
No worries. Does anyone else have any questions, or I'm aware of time, just passing over to Jacob as well.
Oh, we got plenty of time, David. It's all right.
Oh, okay, cool. I think it might be, judging by I'm seeing any more digital hands there, so I'll stop my sharing. I'll jump back in. So obviously, if you wanted a more in-depth demo, that can be arranged as well. You just need to get in contact and we can discuss further any enhancements or features that you might think would be useful. So yeah, thanks for your time.
Thank you, David.
All right.
Cheers.
Let me get my screen up. I assume that's going through all right.
Yeah.
Hi, everyone. So my name's Jacob, and I'll be giving you a quick overview of our multi-resource transport optimization. First, I'll give you just an overview of our standard single resource optimization. So the Dynamic Transport Optimizer, otherwise known as DTO, is a tool that we produce, and it handles modeling and optimization of transport problems. So the software models having a fleet of vehicles and also a collection of orders. And the challenge is to deliver all the orders with the least amount of cost. The way DTO goes about solving the problem is using an artificial intelligence approach. And doing this, it can produce optimized schedules and run sheets, but it can also do things like real-time dispatching. In terms of interface, the input can be just directly an Excel spreadsheet. Otherwise, there's a new web interface. This means that you can modify the input, optimize the routes, and also view the solution, all without leaving the web browser. It can also directly integrate with existing transport management systems and enterprise resource planning software. This streamlines the process and just allows for quick and easy optimization. To give you an idea about the kind of options that DTO supports, here's a few of them. So you can give time windows. Maybe one of your locations can only take orders between 9 a.m. and 5 p.m. So that's a hard time window. You can also do soft time windows, which is the same thing, but instead of making that a strict rule, it will just incur a cost if it's outside of that time window. You can also do fully customizable break schemes. Maybe your drivers need to take 1 lunch break and 2 morning tea and afternoon tea. And there's also options for compatibility. Maybe you've got refrigerated loads that can only go on a refrigerated truck. Likewise, you might only be able to put frozen orders with other frozen orders. This is just a few of the options. There's like heaps and heaps of options. So all this means is that DTO is capable of modeling quite advanced transport scenarios with a huge amount of detail. So that's a quick recap of our standard single resource transport optimizer. I'll go through the interface to that in the demo later. So previously we only had one resource to account for. This was the vehicles and the drivers. In that case, we treated them as one entity. But for many other transport scenarios, the trailer can actually be detached from the tractor. When I say tractor here, it's the prime mover. It's what drives the trailer from place to place. And this scenario comes up in heaps of places. So maybe you're making deliveries to a large supermarket chain. In this case, you're very likely to see bigger trucks that can be detached from the trailer. But you also see it in smaller scale problems. So this might be the case where you've got one driver who can drive many rigid vehicles or many vans, something like that. So this adds an extra layer of complexity to the problem. So the same tractor can take many different trailers, the same driver can take many different vehicles. But it does add the potential to optimize the cost even further. So for example, the trailer can be preloaded with the orders before the tractor comes to pick it up. So maybe it takes an hour and a half to load the trailer, but only half an hour to hitch the trailer on. If the trailer is always hitched, the driver's just going to have to wait around for the whole loading time instead of being able to just pick it up and go. So being able to optimize that is going to reduce costs even further. The situation comes up whenever the mechanism that moves the vehicle, whether that's the driver or the tractor, is distinct from the carrying capacity of the vehicle. So that's either the trailer or the rigid vehicle. Let's have a quick look at how we solve these problems. So the traditional approach to solving this kind of problem is to use a multi-stage optimization process. In the first stage, we assume that there's going to be tractors and drivers available to move the trailers around. And then what we do is we assign the loads to the trailers. Then in the second round, we allocate the drivers and the tractors to the loads that have already been allocated. So in the first step, we allocate the orders to the trailers, and then we actually figure out how the trailers are going to get from place to place. What this is effectively doing is taking a multi-resource problem and then reducing it to multiple single resource problems. And those single resource problems, DTO already has the capability to optimize. So as well as optimizing this traditional approach, we've also implemented a newer advanced approach. So for this new approach, instead of with the trailers, we're going to assume that the trailers will be pretty much available because they're a bit more abundant than the tractors and the drivers. And then we'll optimize with the tractors first. So first we assign the orders to the tractors, and then we actually figure out what trailers that we're going to use for it. So the immediate problem is, and the reason why this isn't the traditional approach, is that some locations might only be compatible with some trailers. So you might have heaps of inner city orders where in the first round of optimization, they're all assigned to a single tractor. But now you've got to use the biggest trailer you've got to fit them all on. Now, since these inner city locations can't handle such a big trailer, the optimization fails. So what we've done to address the issue is we've actually integrated some of the trailer and the driver constraints into that first round optimization. So now, instead of all of those inner city orders being assigned together, they'll actually be split up over multiple different loads so that you can use small trailers. The integration of these constraints is really what allows this approach to work. And there's a couple of reasons why we're doing this. So by optimizing using the tractors first, you end up using much fewer tractors and therefore drivers than before. And since tractors and drivers tend to be a lot more expensive than using more trailers, you end up with a better solution in terms of cost. Also, previously brakes could not be enforced properly for the drivers. What we would have done previously is just roughly subtract the time off the end and then assume that it would work out. But by modeling the driver brakes in the first round optimization, it makes for a much more accurate model. And lastly, the trailers have like quite a relaxed timing constraint. So it doesn't really matter how much you use a trailer. It can be used 24 hours a day. You won't really hear it complaining, you know? But you can't say the same about drivers. So the timing constraints there are much more strict. So by imposing these time constraints in the first round, it ensures that those timing constraints can be met. So I've taken some data for deliveries to a large supermarket chain, and I've run the optimizer using both the traditional and the new approach. First off, we can see that the new approach has a lower cost. So we get a 10% reduction in this case from 230,000 to 207,000. We also see, as expected, that it uses much fewer tractors, down from 58 to 37. This is at the cost of using more trailers. So we go from 31 to 59. But since trailers are a cheaper resource, it ends up being better overall. In the other metrics, we also see that the new approach is better, like total distance, total time used, and the number of rigids used. A rigid vehicle is just a tractor and a trailer that's permanently linked. So the classical single resource. And that's all with delivering all the orders. All right, so let's have a look at the demo. I'll move over to our web interface. So this is the interface to DTO. And you can see that we've got our tabs up here to give our input. The first one's our general tab. This is where you give overall parameters for the optimization. Most notably here, we've got the tractor trailer mode. So this is where you tell it whether you want the traditional approach, which is the trailer first, or the new approach, which is tractor first. The default here is it will run both and then decide which one it thinks is best. But the option here allows you to compare and contrast them. We've got our list of locations, pretty self-explanatory, but this is just all the locations where the orders are going to be picked up from or delivered to. You can feed it an address, and then we use a geocoding service like Google Maps or Bing to get the coordinates for that. We've got the orders that need to be delivered. So in here, there's things like the amount of volume that this occupies and the time it takes to pick up the order or deliver the order and where it needs to be delivered. Here's the tractors. So here's our prime movers. And you'll put in constraints like the earliest start time, latest start time, how much they cost, what brakes they need. And the big addition here is we've got the trailers tab. So these are the trailers that are available to be used, and you'll input things, the same things as before, like earliest start time, latest start time, the amount of time they can be used for, how long they take to hitch and unhitch, and of course our rigid vehicles. So let's go in and hit solve. So the scenario I've got here is a smaller version of the supermarket delivery problem that I had before. So we can see all the orders on the map here. And I'll hit solve. Shouldn't take too long. And that's done. So straight away we can see that all of our markers here have gone green, which means all of our orders have been delivered. And if we go here, we can actually go through and view the routes that all of our vehicles take. So here's prime mover 1, and that's where it goes. Let's have a look at prime mover 2. So this one will start at the depot here, and it's going to pick up this trailer, 22P02, and that's already going to have order 7 loaded on it. And then that one will go down to here and get delivered along with the trailer. So this is also shown in the run sheet. So the run sheet here shows the run sheets for both the prime movers, the rigids, and the trailers. So once again, we can see that prime mover 2 starts at the depot, picks up the 22P02 trailer. And in the 22P02 run sheet, we can see that that one has picked up order 7. And just quickly, we can have a look at the key performance indicators as well. So we can see here that you get things like the amount of work time, transit time, distance, things like that. So that was a quick look at DTO and the multi-resource optimization. To give you a quick summary, so we've implemented both the new approach and the existing approach, the traditional approach, to solve these tractor-trailer optimization problems. The new approach uses the tractors first, which is the real key innovation that we've developed. And what this allows us to do is to better satisfy the timing constraints. That's because the timing constraints on the drivers are more strict. It also allows us to properly model the brakes on the drivers. And lastly, it optimizes the use of the more costly resources a lot more heavily than it does the more cheap resources. And that's all I've got to show.
Jacob, I think Paul had a question on the chat about how we define a rigid. Was that right, Paul?
Yeah. Sorry, it was just on that main screen where you had the tabs of the trailer and the and the tractor. And by the way, of course, tractor is a very American term. In Australia, we call them prime movers, right? But that's I'm sure that's an easy change.
Yeah, absolutely. Yeah. So do you mean as the...
Sorry, that previous screen you had open, yeah.
This one here?
Yeah, where you've got tractors and trailers.
Yeah.
Yes, so the rigid would be...
I've got the rigids are in here at the moment. Yeah,
as part of the trailer.
There was a decision as to whether to put it under the tractors where they probably more properly belong, or whether they go under trailers or under their own tab in their own right. At the moment, they're just under trailers, but it's just a representation thing.
Yep. No, that's good. Yeah. That's fine. Yeah.
In fact, I mean, Jacob, it's rather academic, isn't it? Because you can define costs for both types of entity. So you can still put things like driver salary in the rigid as you can in the prime mover. So
exactly,
like operating cost and one-time cost and all that sort of stuff. And I think Peter Honeyman, you've got something in the chat.
Multiple pickup locations.
Yeah, hi there. I'm just wondering if you could, obviously you go to a supermarket and do an unload, and then can you do a diversion and do a pickup and then come back to the depot again?
I may take this one. If you...
Yeah.
So in terms of, it won't allow you to do multiple pickups in the same load from different DCs, but different loads can be picked up from different DCs. So you may drop off your, do a load, drop off your trailer at a different DC as from where it came from, and then pick up another trailer there, and so on. So that's probably the most common scenario. So I'm not sure if you mean that sort of thing, which we tend to call a roaming fleet, or whether you're referring to picking up from within the same, like picking up in one DC, then drive to another one, pick up some more. Because if you do that, you really don't gain the advantage of the preloading.
Now, the idea is that you would drop the the secondary load at the supermarket and then go and pick up a primary product to actually bring back to the supermarket, so that I guess you're maximising your fleet on the back, the empty back load, if you like.
Yeah, I think, Peter, that's standard pickup and delivery, really. So I think we can do that. We just configured it for this use case. But we can do standard pickup and delivery, which is drop off, pickup, ad infinitum.
Yeah, I mean, we'd have the order along with the secondary orders. We'd have the orders, that I guess we just want to be able to use the fleet, I guess, when we're returning home as well, instead of just coming back empty. If there was a location that was close to the supermarket you did the unload at, whether you could divert 5 kilometres and then pick that up and then come back to your depot.
Yeah, well, yeah, in fact we already did this as a proof of concept for one of your guys, which was delivering to Bunnings for timber.
Yeah.
And we pick it.
Yes,
it was identifying ad hoc backloads based on a list of backhaul and the constraints around the delivery time of the backhaul and making sure that the driver had enough hours to actually get all the way back to base.
No, sweet. I was just making sure that was awesome.
And it's really around. So you can always treat the tractor and trailer as a single resource in at least part of your solution, but it's really around where can we make the most of preloading. So you may be preloading your trailer, then a tractor would come in, hook up with the trailer, go and do a delivery. Then the tractor may stay with the trailer to quickly load something that's going back to the DC, and then basically not do that hitch and unhitch operation. And it really depends on how long it takes to load versus the hitch and unhitch operation.
Yeah, I mean, it's kind of using multi and single resource. You're multi at the start, whilst you're waiting for the trailer to be loaded, the driver hitches up, takes the load to the supermarket, unloads that, and it's just then convenient to stay hitched together. Obviously you have to stay with the trailer whilst you load the next product that's heading back to the DC, and and then obviously when it gets back, the trailer's unhitched and the driver moves on.
Yeah. So that's something we quite commonly see, or even where they're just only preload at the start of the day.
Leslie, I wonder, can you have a look in the chat, because there's a few more questions.
Yeah. Okay.
So be able to address.
Yeah. So there's a general technology question on. So all of our optimizations basically use the technology based on constraint programming and artificial intelligence. We have the capability to use technologies like mixed integer programming, and we have used linear programming in some applications, but for the most of it, and that includes both this one and what David was presenting, it's a combination of constraint programming and AI techniques. There's a question around live traffic information. So we can use multiple mapping providers. So we use OpenStreetMaps generally for the optimization, which is because using commercial providers like Google or here Maps is highly restricted in terms of how many source and destination pairs you can you can send to it. And we need to run this very quickly, so we need something that we have a full control over. We have the option though to use in particular Google Maps for then recomputing the ETAs once we've done an optimization and look at live traffic information. I'd have to point out though that even with Google Maps, you really only get the information on what it's looking like now, and not necessarily what it's looking like 2 or 3 hours down the track. And as we are producing multi-leg journeys, we can use Google Maps for the first leg, which is happening sort of at that moment, but we'd still have to use estimates as to how long the remainder of the journey would take. And then there's one more.
Sorry, Leslie.
Yeah.
I think you're being slightly complimentary to Google there. I mean, I think our experience with Google as a provider of routing data is basically they're too expensive and they rate limit their service too much to be useful. So it's not necessarily all that economic or indeed practical to actually use them. I think the other thing is our experience with this is rather than trying to compute transit times, predict traffic conditions ahead of time, like my video, actually what is more effective is to actually recompute as the day progresses to account for things like traffic delays and so forth.
Yeah, plus the other big thing is that we can re-optimize. So if things do change, we can actually we can replan and see if we can make changes to the original plan based on not being able to meet time windows again or so on. There's one final question around so in the multi-stage optimization, when we do the planning for the tractors, what sort of capacity we use for the for the trailer during that process. So that's an interesting question, because that's really where we differentiate ourselves and where we have specific features to make this work. So what we do is the tractor could have we can restrict it to certain types of trailers. So we can have certain tractors for B doubles versus single trailers. But as to the actual trailer capacity, basically we set it to as big as the tractor can move. But then we look at what are the different restrictions at all of the sites I'm going to visit during my load. So let's say my tractor can pull a 24 pallet trailer, but I'm visiting a 16 pallet max store, so a store that has a loading bay that's not big enough to cater for any larger vehicle. Then it will make sure that that load is not bigger than those 16 pallets. So it dynamically adjusts the capacity based on the locations it's visiting while it's doing the optimization.
Okay, thanks, Leslie. We're just about, I think we're getting towards time. So were there any other questions or any comments? And please come direct if you want more information, if you don't want to ask in a public forum. Paul, yeah? Oh, that's a
Thank you. No, it was
That's
excellent.
all right.
Really appreciate it. Yeah.
Okay, that's no worries.
Yeah.
Well, look, it's been a very interactive session, actually. I'm very pleased that we've got some feedback, and look, any comments that welcome, just either email me or Leslie or Jacob, or and look, if there's any opportunities that you'd like to discuss, just reach out, and we'll have another one, Tara, probably what, in 2-3 months time?
Yes, I think 6th of September, the next one.
That's a bit precise. Yeah, so we'll aim for September. And if there's any topics that any of the audience would like us to address, because we've really got too much to say often, we're happy to do that.
Cool, thank you.
Thank you,
All right.
Alan.
Look, anyway, I'll close the meeting now, but look, thank you very much for coming. Really appreciate your input and your time, and look forward to catching up again in September, if not before.
Terrific. Thanks, guys.
Thanks very
Much
much.
appreciated.